Okay. Hi, good morning, everyone. I'm sorry for being a little bit late. Suddenly, Columbia is closed. That's unfortunate. So today we're going to continue talking about SN1 and SN2 reaction mechanisms. We will continue talking about SN1 and SN2 reaction mechanisms, and we stopped on this slide last time. And before moving on, let's summarize everything and talk about polarizable versus non-polarizable, basically effect of the size of the atom in different solvents on the nucleophilicity. So just to summarize everything, you remember that we discussed SN2 reaction, that stands for substitution nucleophilic bimolecular. In this reaction, you have a molecule with some group, and group X will be a leaving group. And good leaving group should be, as X minus, should be a weak base. This would make that electrophile suitable for SN2 reaction. Then you should have some nucleophile, and nucleophile should be better for SN2 strong. And that reaction occurs by nucleophilic attack of the electrophilic center delta plus on the carbon and breakage of the bond CX with the formation of a substituted product and the leaving group in solution. This reaction occurs through one transition state without intermediates. So if this is reaction coordinate, this is energy, reaction will look something like this, where this would be transition state, where you will have formation of nucleophile C bond and breakage of nucleophile leaving group bond at the same time. For this reaction, your nucleophile should attack from the opposite side from which the leaving group leaves, because nucleophile needs to attack an orbital. And we don't have any empty orbitals other than antibonding for this carbon, because this carbon has already 4 bonds. So all orbitals, or all possible electrons and orbitals on the valence shell of this carbon is already filled. But we have antibonding orbitals that are molecular orbitals from the bond. And our nucleophile can attack that orbital, and that orbital pokes from the other side of, so if, if this is our usual sigma bond, like CX, our antibonding orbital will be over here. And this is where nucleophile attacks, and this is why it attacks from the back. And due to that specific attack and the fact that our transition state is actually kind of 5 coordinated carbon, it's not, this carbon doesn't truly have 5 bonds. It has 3 solid bonds and 2 half bonds. But basically, we have change in stereochemistry after that reaction. So if we started, let's say this would be ethyl, this would be ethyl. If we started with leaving group being on the wedge, after the reaction our nucleophile will be on the dash. And generally speaking, if you had S stereoisomer, you should form R1. But there are some exceptions that we went over during the last lecture, and it was the case when we are substituting something like Br with high atomic number to Cn, where you have carbon, and you have a change in priority of the substituents. So keep an eye on that, whether your priority of the substituents changes or not after the substitution. But if it's not the case, then S will become R and R will become S for the stereocenter. This reaction rate of this reaction depends on many things. It depends on your electrophile, so initial molecule we're starting with. For electrophile, for good electrophile, we want to have something that is not sterically hindered. So for electrophile, primary would be better than secondary, would be better than tertiary. But other than that, what else we have? We have allylic, vinylic, benzylic, and aryl possibilities. And with tertiary electrophile, this reaction almost, like, I would say it's either negligible or it doesn't occur at all. So what else we can put in the category no reaction occurs would be this one, and that would basically a bond, not a carbon. And this one. So if your carbon atom is sp2 on which you are planning to do the substitution, don't. So if your leaving group, like not your leaving group, a group that you think can be a leaving group is attached to SN2 carbon atom, there is no sp2, I'm so sorry. There is no possibility of the reaction. However, if you have something like this, your reaction actually will occur faster than even with, excuse me, not this one. Okay, so this would be even better than primary, because conjugate p orbitals can help to stabilize the transition state. We had it on our slides, or it will be either one slide back or a couple of slides further, like the actual drawings, how it occurs. So we either will, because we went through it last time, but I believe I had to scroll through the presentation a little bit to get to that place. Basically, electrophile matters. This is the from most reactive to least reactive types of electrophiles in the slide. So structure of electrophile matters. Also leaving group matters, because the better the leaving group, the weaker the leaving group as a base, the faster reaction would be, the better it would leave. And another factor is nucleophile. For nucleophile, generally, same rules apply as for bases, with a few exceptions. And those exceptions are based on the difference in the interaction between that base wants and nucleophile wants. So your base wants proton, your nucleophile wants to attack positively charged, partially positively charged carbon. And because your proton is small, sterically unhindered, and easy to access, bases have very clear and straightforward strength dependence. But for nucleophile, there are a couple of things such as sterical hindrance of the nucleophilic center that would affect. And this was something that some of you didn't get from the last lecture. It was in the quizzes. If you have third butoxide and etoxide, those two. Etoxide would be strong base and good nucleophile. It would be good nucleophile because you have electronegative atom with negative charge, small steric hindrance from acyl group, everything looks wonderful. But when we look at butoxide, it would be a strong base. It will be extremely strong base, very good base. But it would be very poor nucleophile. Why? Because of that butyl, it is so big that it actually doesn't allow that nucleophile to access the partially positively charged carbon due to the steric hindrance. So steric hindrance is bad, and I would say that examples of that other than butoxide is, maybe you remember we were drawing LDA at some point, so something like this with two isopropyls. Also, you can notice that two isopropyls is kind of rather big groups, and there are two of them. So something like that also would be very strong base and very poor nucleophile. So that matters. And about polarizability and different solvents. So the thing is that overall trend and basicity for example, halogens would be that fluoride would be the strongest base and iodide would be the weakest base, right? Because your HI would be the strongest acid, so its conjugate base should be the weakest. And that trend in terms of the basicity will be the same for nucleophilicity if we work in aprotic solvents. So your F- would be the best nucleophile if we work in aprotic solvents. Yes, it's Hello Tuesday's lecture. I don't know what made me so confused. It's that easy. But if you have protic solvents, especially like protic solvents that can form hydrogen bonds, those would form a solvate shell around your. That's not funny. It's 8:30 a.m. And what is the question?
Let me just work out what's a protic solvent.
So it's a good question to ask. I mean, maybe for everyone, because not like probably not everyone remembers, and it's okay. It happens again. It's 8 a.m. Maybe 9 already. So your protic versus aprotic solvents. Protic solvents are solvents that can form hydrogen bonds, so they can be both lone pair donors and hydrogen delta plus charged hydrogen donors. Aprotic solvents don't have that delta plus charged hydrogen. So, example for that. One second, where to put it? Okay, let's say methanol. Methanol has electronegatively charged oxygen with lone pairs, and it has hydrogen with delta plus. Obviously, methanol can form hydrogen bonds with itself, right? This is polar protic solvent. And protic, like proton, hydrogen bonds, this can be a correlation. But if we will look at acetone, which is polar aprotic solvent, it is also polar. It also has a dipole. But here we don't have any hydrogen that is attached to electronegative atom. So acetone cannot form hydrogen bonds with itself. Yes, if we will add some water or methanol, yeah, there is a possibility, but that would be for, I would say, all polar solvents. So this is difference between protic and aprotic. And what happens if we take protic polar solvent? Protic polar solvent can insanely good stabilize charged species. So if you have cation or anion, protic solvent knows what to do and how to stabilize it very good. And if you have fluoride, which is F-, very small concentrated charge, that doesn't feel good in solution. And if you will put that in a protic medium, you will have a lot of like methanol or water atoms, bless you, arranging around that small negatively charged fluoride, thereby compensating the charge and kind of hindering it, like putting a coat on it. And it becomes much worse nucleophile. So if you work in a polar protic solvents, 1 second. And okay, here. In the protic solvents, we will have F minus would be worse than Cl minus, worse than Br, worse than iodide. And same would be oxygen would be worse than sulfur. And first of all, probably you remember about hydrogen bonds. We mostly were talking about fluorides, like fluorine in general, that it can form hydrogen bonds. But those interactions, like delta negative, delta positive interactions, can be applied to all halogens in general, because even if you don't have like true hydrogen bonds, you can have still that strong dipole stabilization of the charge from the protic solvent. And this is why with the decrease of the interactions of the solvent with your nucleophile, the nucleophilic strength will increase. Because iodide would be big, soft, it will feel comfortable, it won't need a lot of solvent molecules to help to stabilize it. And also here polarizability kicks in. Iodide would be big and very polarizable with big orbitals that, like I showed it to Helen, like let's imagine this is fluoride, and it has like a coat of solvated atoms, and somewhere here is your center. And like it's not very aggressive, obviously, because it has that stabilization by water molecules, and it cannot reach the electrophilic center. But this is iodide. It has big orbitals that can easily overlap. It doesn't have a lot of water molecules or like solvent molecules around it, so it can easily come, reach, and overlap and do the orbital overlap for the reaction. And this is for polar protic solvents. For aprotic solvents, because in aprotic solvents the stabilization of negative charge is much worse, you will have still the same logic as in bases. Your fluoride will be stronger nucleophile than iodide. Yes?
So like for example in the quiz where we're directly comparing like oxygen versus sulfur, what it like without knowing what our solvent is, we wouldn't be able to answer that.
True. That was my bad.
Okay.
Because like the thing is that discussion of the solvent effect is usually like it's not secondary. It's somewhere there. And like I a little bit forgot about that thing because and like it's my bad that I forgot about that thing, and I feel very bad. And you make me feel very bad, but again, I hope today we covered it well, and also I will, because of that, so no one will be confused, for example, someone who was in the previous lecture but is not here today, I will make basically a summary flowchart thing, like I did for enantiomers versus meso, all of that. I hope this will be helpful. Basically, how to understand what the good acid reaction is. So you can actually go through and see all the factors there. So it will be summarized on one slide. I will also do that and post it on Learn. Yes?
Is the solvent always polar? Could it be like non-polar?
No, non-polar solvents is not a good thing for any of those reactions because first of all, your materials, all of them, should be soluble in your solvent, right? Because this is a job of the solvent. But your good nucleophiles are usually charged. Charged species and non-polar solvents do not go together. They don't like it. Also, your transition state, like obviously your solvent usually, okay. So it is very important to stabilize transition state or intermediates. So not even products and reactants, they should be soluble, but it's very important to stabilize all of those intermediates and transition states. And transition states here is very, like it has delta plus in the middle, delta minus on the nucleophile, delta minus on the leaving group, so is partially charged, and if you will take non-polar solvent, that transition state will be extremely bad in energy, and your activation energy will be just through the roof. So this is why we don't even consider non-polar solvents for reactions like SN2 and SN1. And here, difference between protic versus aprotic, it starts with polarizability, but polarizability in general is a good thing. So if so polarizability cannot trump in aprotic solvents the base strength, but still polarizability is a good thing, regardless of the solvent. Polarizability is a good thing. So, for example, a lot of good nucleophiles, they have S minus, for example, and they undergo SN2 reactions very easily. Yes.
Does that include like the polarizability of like the whole molecule, like the whole electron?
No, like the nucleophilic center,
Okay.
like sulfur or iodide.
Okay. So I'm just wondering, like, you have a longer chain, but that like because it's more polarized, but like more of the electron density could move towards like the nucleophilic center.
No, it's not mostly about that. It's like, it's mostly, I would say, about size of the orbitals and then the atom. I believe it was, 1 second, let me just open this. 1 second. It was somewhere here. Ooh. I just want to open the slide with, where is it? It was somewhere here. I saw it. I recently saw it. Here, this one. What? Where? Hold on. It's like more about, basically the orbitals of the nucleophilic center. It's not like this. It's
Slide
not about
18 of the
it's about
lecture.
polarizability in terms of the whole atom bearing the negative charge. And you can, like, I don't have it on those slides, but there are very fancy like electron density distributions in iodine versus like fluoride on Google. I'm pretty sure I saw it maybe a year ago, and in my head I believe I saw it. It wasn't a mirage. So it's all about that more efficient or not efficient overlap. And when we talk polarizability, it's about basically size of those orbitals, and then they can overlap and interact better with the electrophilic center. So, yes.
Yeah, so like to summarize, like if you're in an aprotic solvent, then it's exactly the same as bases with the exception of steric hindrance.
Yes.
And then in protic solvents, it's steric hindrance and polarizability with exception.
I would say not polarizability, it's hydrogen bond destabilization, not destabilization, stabilization of negative charges. So the more concentrated, the worse. So it just, a second. Right. Okay, so do you remember, so let's disregard steric hindrance right now. So for bases, it would be from right to left, right? So your F minus would be a weaker base compared to C minus. And it would be from bottom to top. So here is, and C minus. This is trends for basicity. Same trends would be for nucleophiles in aprotic and nucleophiles in protic. It would be same here, but like that. Right?
Yeah.
Cool. Cool. And also why it brought me a little bit of, not I would say confusion, even though we're talking about protic solvents here, you won't see protic solvents for SN2 like almost never. The issue here is that for your reactions in organic chemistry in general, they won't go as you draw them on a board. We can draw whatever we want and say draw whatever diagrams we want. Reactions will go first of all the way they want it, and second of all, usually in organic chemistry you will have multiple products. That will be a result of several different mechanisms of the reaction. And your protic solvents actually, they will stabilize intermediates for SN1 reaction that occurs differently than SN2. And this is why basically to suppress all possible E1 and SN1 mechanisms, we usually choose aprotic solvents for SN2 reactions. So that all the solvent part, discussion part, even though it is crucial for the overall reaction review, it's not quite useful in terms of the applicability. Okay, so where were we? Wonderful, perfect, glorious. Okay. So how do you guys feel about SN2 right now? Is it at least a little bit clearer than it was after Tuesday? Because I felt that after Tuesday it was a hot mess and I was like even said and I was thinking what to do with that. I think when we will discuss SN1, let me try to say what I'm trying to say first in terms of the logic, and then we can discuss your questions, because what was also the issue on the previous lecture, because some of you, and that's great that you read read the material, the course notes, but you were asking questions that I haven't yet started to talk about, and they're like in 5 slides, but I'm answering this question right now, and then 5 slides later, I'm kind of missing certain points because I already talked about it like 10 minutes ago. And it all becomes a hot mess, and I want that to go as smoothly for you as possible. Okay, so basically when you see a reaction, and we will talk about competition of SN1 and SN2, but right now I just want to start introducing you how to understand what should trigger your understanding which reaction will occur. Because obviously on your final you won't have SN1 versus SN2, you will have a lot of reactions in your head. And you need to work on finding triggers for certain reactions. So for example, you see here you have some alkyl halide with methoxy group. And when you see halide, usually halides are a very good leaving group. So it can give you a little hint that maybe it's something about substitution or elimination. Then you look at your reactants, at your solvent, which is below the arrow, acetone, and sodium cyan. And what you can say, acetone, it's polar aprotic solvent. And as I said, for SN2, you will see polar aprotic solvents like 99.9% of the time. I'm not saying 100, I'm just saying that it would be quite often, very often. And sodium cyan, like the Cn minus, you can start remembering it from now on. Cn minus, very good nucleophile, you will see it a lot. Usually, if you see something like alkyl halide, Cn minus, and acetone, it is SN2. And it will be SN2. So this basically combination of regions highly likely will be SN2. So let's look at the molecule on the left. We have possibility for 2 different leaving groups. Which one you want to detach from a molecule? Which one you like more as a leaving group?
Bromine?
Yes. So we need to look at the basicity And obviously this would be a weaker base, and we love that. So we will have a backside attack over here. And you see how the stereochemistry changed. So we had those in plane lines with the angle to the right, and right now the angle is to the left. So the overall steric of the center switched. So again, reaction mechanism, if we will draw it shortly, as I drew it here, quite easy. We can also draw it through the transition state, and if you're asked to draw a transition state, you can do it like H2, H5, Dr. And that can be also dashed trace. I mean, it's not dashed here, but like, let's imagine it's dashed. So you see that here, when you draw the like, here it's on the dash, here it's on the dash. In this transition state, you draw it like that, and then your leaving group and your nucleophile basically point through it. You don't, like, I don't draw wedges and dashes here. Yeah, you can technically. Yeah.
When you're drawing the transition state, like, you have to write the charges, so then you can use like, because like if you look at it, you have 5 kind of carbon.
You can draw something like this.
Okay.
Like, you can draw charges. What I said that you should.
Can you assign formal charges, or does that not make sense?
But what is formal charge? Like, what is charge? What is charge?
Like,
pair of electrons.
Yeah.
What's going on with pair of electrons in this transition state?
Well, I guess they're moving.
They are moving, so you cannot say like they are here, because one bond is forming, another bond is breaking. This all is very dynamic. So this is why use dashed line. Just I draw a solid line because I don't know, I was in a hurry, but that will show you that the bonds are not actually there. They are kind of there. They are not fully formed. They are not fully destroyed. And you can put delta minus, delta plus, sure. And you can put wedge dash for the transition state, but also you can just draw it as like plain 3 lines in one plane, because it is assumed that those 3 lines, they will be flat, and your leaving group and your nucleophile, they will basically poke through that plane with 3 atoms. So also something I forgot to mention when talking about solvents and doing that recap about protic versus aprotic solvent effect on the reaction diagram and activation energy. So, and this question has an acetone versus ethanol, so it's nice to mention that effect. So acetone versus ethanol. Ethanol, protic, this one is aprotic. What will happen in a protic solvent? Your sodium CN will be more stabilized. So your reaction coordinates, your reactants will actually have lower energy because your anion is more stabilized, so overall energy of your reactants will be lower. And then you will need to undergo activation energy and you will form your products. That will be transition state, and that would be FOH. But if we, instead of ethanol, we will take acetone, acetone will do much worse job in the stabilization of CN minus. So our acetone, our energy of the reactants in acetone will be somewhere like here, for example. So it would be much higher. And transition state energy also will be a little bit higher, but not that much, because transition state is not charged, it has partial charges, and it requires less stabilization by like hydrogen bonds or whatnot compared to the CN minus. So CN basically effect of stabilization by a protic solvent will be much higher, much greater on the negatively charged nucleophile than on the transition state. This is why differences in energy for reactants would be big, and for transition state there will be some, but it will be small. And ugly, but it doesn't matter. So, and this is products again. Our products will also have negative charge, but the difference again will not be so big because we will form a weaker base, which should be more stable by itself even without additional stabilization. And what happens here? Here our activation energy for acetone is much smaller compared to activation energy for ethanol. And that difference arises from the difference of the stabilization of the nucleophile. And obviously, the more nucleophile is stabilized, the more energy you need to put in the system in order to make that nucleophile to go and react with your electrophilic center, right? So this is the difference that I forgot to mention on the summary slide about different solvents. Okay, is this clear for everyone?
Mm-hmm.
Yeah? Yeah.
Sorry, I didn't get why, okay, so ethanol is protic and it has a bigger activation energy, so it's better for the reaction?
No.
No? Am I off?
So the smaller activation energy, the faster the reaction, right?
Okay.
And in acetone, reaction will occur faster. In ethanol, reaction will occur slower. Because for ethanol, you will have higher activation energy because stabilization of the nucleophile will be greater there due to the hydrogen bonds and your polars, protic are usually more polar than a protic polar solvents.
Okay.
And I would say when we choose good or bad solvent, in general for the reactions we're going to discuss in a close future, first thing we need to do is to make sure that everything is soluble in those solvents. And to be honest, you may smile right now, that can be a problem. And second thing is, by choosing polar protic or a protic solvent, you can actually turn the way how your reaction will go, because again, several reaction mechanisms can occur at the same time. And if you will take protic, here you will have higher activation energy, and for SN1 you have lower activation energy, and SN1 only occurs in protic solvents. So SN1 will become a major one, and SN1 mechanism is very different from this one.
Okay.
And this is why we should choose solvents based on what reaction wants. Like obviously if we don't have any possibility of the side reactions and we have just like red pill, blue pill, like ethanol, acetone, probably I would choose acetone because I like lower activation energy better.
Okay.
But I hope you get why we have that lower activation, like not you personally, I mean like you with a small y, why the activation energy is smaller for acetone. Okay, I just have a few minutes. We will look through electrophiles one more time. We had it during the last lecture, but again, the less sterically hindered your electrophilic center is, the better for the reaction. Because you need to take nucleophile and basically show it towards the carbon. And obviously access to this carbon would be much less hindered compared to this one, and so on and so forth. And when you see tertiary, forget that SN2 exists. And here. And we also looked at this one, but it was like maybe 5 seconds on the board, so I decided we need to look through it again. Let's imagine that those diagrams with gray circles, it is what nucleophiles see. So this green ball is your living group. White balls are your hydrogen. Blue ball is carbon, that is your electrophilic center. And this red place is from where your antibonding orbital, like where is the access to our antibonding orbital is. So basically a goal for your nucleophile to get to that red spot. And if we start to have more and more substituents instead of hydrogen, so we have 1 methyl, 2 methyls, 3 methyls, you can see how harder it becomes to get access to that red point, right? And the more substituted your electrophilic center is, the higher would be the energy barrier for that reaction. And at some point, for tertiary, for example, it is so high that the reaction doesn't go. Because it's like physically impossible to take nucleophile and put it there. It's theoretically impossible. And again, some rates, and when you see tables like that, how to read them? It's quite easy. The greater the number, the more reaction occurs. So if you have 145 versus 1, it means that rate for the methyl bromide would be 145 times faster than that for ethyl bromide. And here on the left, there is a substitution for alpha carbon. And what is alpha carbon? You have your substituent Br. Br is connected to a carbon, and that first carbon atom your group is connected to, it is alpha. The next one would be beta. The next one would be, what is this, gamma. So this is beta carbon atom, and there is no substitution here on beta, all on alpha. And you see how drastically substitution on the alpha carbon atom changes the reaction rate. However, when we have substitution on the beta carbon atom, that effect is much smaller. Because it is further from that additional sterical hindrance, it is further from the electrophilic center, thereby access to the electrophilic center is easier and reaction is faster. Okay. Because we don't have time, we'll talk. Yeah, and this is the last one, and after that I will leave. So this is a summary table, well, not table, summary graph, drawing, whatnot, on the page, well, it's like 151, 152, with different electrophiles in their strain. And here you have relative rate, something we just guessed.
In the Tuesday's quiz, I believe there was like a double bond of carbon in the electrophile rate, like electrophile ordering. How does the double bond affect the reaction rate for that?
What was the last part of what you asked?
So like there was a question to rate or electrophiles, right?
Yes.
And there were the primary, secondary, tertiary
Yes.
Electrophiles, but there was also a double bonded
Like vinylic,
It's
vinyl,
vinyl and
anilic,
out.
yeah. And this is why I
It's in
opened that
it's in those
side of
examples
survey
right
as
now.
well.
okay.
Because this is your vinyl. Vinyl, basically, when you have double bond and something is directly connected to double bond without other carbon. So your Br is connected to sp2 hybridized carbon atom. This is vinyl. Allylic is when you have a double bond, then you have sp3 hybridized carbon, and only then something is connected to it, right? Same logic, benzylic and aryl. Logic is same. Here for aryl you also have sp2 hybridized carbon with direct connection to Br. And for benzylic you have sp3 hybridized carbon between those between the conjugated system and Br. Allylic and benzylic in general are very good for cations, anions, as electrophiles, all of that stuff. They do it wonderfully, beautifully. And you can see here on the relative rate, allylic and benzylic have higher relative reaction rates compared to methyl. So if you have methyl bromide, it will react slower than allylic or benzylic electrophile. And benzylic electrophile will react very fast. But vinyl and aryl, the one with the Br connected to sp2 directly, they won't react at all. And you can see that here for secondary, relative reaction rate was slow, and you can imagine that tertiary also will be like 0, just like vinyl and aryl for S2 reactions.
And the reason for that is just resonance, right?
No, there is no actual charge. There is additional stabilization. So here, this one, this was the cartoon I was talking about when I mentioned the electrophiles. So quickly, this is your electrophilic center, your carbon on which reaction occurs. This is your leaving group. This is your nucleophile attack. This all is transition state, right? This is 1 substituent, 2 substituent, 3 substituent. And that third substituent, it has those 2 p orbitals that form a pi bond. And because of the geometry of your transition state, because you have basically a plane through which you have that basically a line on which the leaving group lives and the nucleophile attacks, geometrically, your formed bond nucleophile with carbon will be aligned with those p orbitals of the pi bond. And it won't be a resonance, but it would be a conjugation, kind of. So your orbitals will feel each other and they will stabilize each other. And same would occur for nucleophile that is coming and for leaving group that is leaving. Their bitransition state will be additionally stabilized by the effect of the neighboring double bonds. You can look, I believe that is also, like, those cartoons are also in the course notes. You can just actually slowly look at that one, at that cartoon, because actually it depicts everything very good, but you need to like actually sit and look and understand where everything goes and what happens. The bottom line is the p orbitals that form pi bond help to stabilize the transition state through the orbital kind of conjugation. It is something similar what we had for you tell me, I will tell you. I forgot the word, but basically orbitals help each other, cool. And when you have your, why allylic is a little bit worse than benzylic, because in benzylic you will have even more p orbitals, even more conjugation, even more stabilization, it would be even better. That's the bottom line. So I would say for many different reactions and things in organic chemistry, if you have allylic, benzylic, it's the best. Then depending on the steric hindrance, it would be from tertiary to primary or from primary to tertiary, depending on the reaction. And then it would be vinyl and aryl somewhere in the end. Okay. Sorry.